For over a century, we've been burning fossil fuels like coal, oil, and gas to power our cars, our homes, and our factories. This has increased the amounts of CO2 into our atmosphere by 100 ppm. Now, the total amount of CO2 along with other greenhouse gases traps heat from the sun, and the whole planet could experience overheat. Glaciers and ice sheets are melting and could cause sea levels to rise, although the observations are not always consistent with climate models. This is where carbon capture technologies come into play. They are like giant vacuums for the sky, designed to remove CO2 so it can no longer contribute to warming our planet. It's a massive engineering challenge, but it's one we could take on if we trust that CO2 is the problem. It's about ensuring that the world we leave behind for the next generation is healthy and stable. Developing and using carbon capture technologies is a critical piece of that puzzle. It's not a magic bullet that solves everything on its own, but it is an essential tool in our toolbox. We need to understand how these tools work, what they cost, and how we can use them effectively to tackle this global challenge head-on. The two main contenders in this carbon capturing quest: carbon capture and storage, or CCS, and direct air capture, or DAC. They both aim to grab CO2, but they do it in very different places. Imagine you spill a carton of juice. CCS is like wiping up the spill right as it happens, right at the source. It attaches to a big source of pollution, like a power plant or a cement factory. As these places burn fuel and create CO2, the CCS equipment grabs that CO2 from the exhaust fumes before it ever gets a chance to escape into the atmosphere. Direct air capture, or DAC, is a completely different strategy. It's like trying to clean up that same juice spill after it has evaporated and spread throughout your entire house. Instead of capturing CO2 at the source, DAC technology pulls it directly out of the open air, the very air we breathe. It uses giant fans to move huge volumes of air through special filters or chemical solutions that are designed to trap only the CO2 molecules. It's a much tougher job because the CO2 is incredibly diluted out there. DAC is trying to remove the historical emissions. So, let's break it down. CCS is a point source solution. It's preventative. It stops new CO2 from adding to the problem. Think of it as putting a filter on a smokestack. DAC, on the other hand, is a cleanup solution. It's remedial. It removes the CO2 that's already out there, spread all over the globe. It's like a giant air purifier for the entire planet. Both methods end with the same step: taking the captured CO2 and storing it deep underground in geological formations, where it can't escape back into the atmosphere for thousands of years. The key difference is where they get the CO2 from. CCS targets high concentrations of CO2. The flue gas from a power plant can be over 10% CO2. DAC, however, is sifting through the regular air where CO2 makes up only about 0.04%. That's just 400 parts per million. It's like trying to find 400 specific grains of sand on a vast beach. This fundamental difference in concentration is the main reason for the huge gap in their cost and efficiency, which we'll get into next. Now, let's talk economics. Why is DAC so much more expensive than CCS? It all comes down to that concentration problem we just talked about. Let's use another analogy. Imagine you're trying to collect strawberries. CCS is like picking strawberries from a neatly planted field where they are all packed together. You can gather a whole basket pretty quickly and without much effort. DAC, however, is like trying to find the few wild strawberries scattered across a massive forest. You have to wander for miles, using a lot more time and energy just to find a handful. That's why DAC is so expensive. The numbers really tell the story. Capturing 1 ton of CO2 using CCS technology at a power plant or industrial facility typically costs between $50 and $100. It's still a significant cost, but it's in a range that industries can start to manage. Now let's look at DAC. The cost to capture that same ton of CO2 directly from the air is currently somewhere between $600 and $1,000. That's about 10 times more expensive. This huge price difference is almost entirely because of how much energy it takes to move all that air and how complex the chemical processes are for grabbing those few and far between CO2 molecules. Let's look at some real-world examples. In Texas, Occidental Petroleum is building a massive CCS project to capture CO2 from industrial sources and store it underground. These projects are scaling up because the economics, while challenging, are workable. On the DAC side, you have pioneers like Climeworks, which operates a plant in Iceland called Orca. It's an amazing piece of engineering, but it's very expensive to run. They are working hard to bring the costs down, but it's a long road. The world's largest DAC plant, called Stratos, is also being built by Occidental in Texas, showing that some companies are betting big on its future. The energy required is another major factor in the cost. Both technologies need a lot of power, but DAC's needs are enormous. To capture the dilute CO2, DAC plants must run massive fans and constantly heat up materials to release the captured CO2 for storage. CCS also needs energy, but since the CO2 is already concentrated, the process is just more efficient. This cost and energy reality shapes how we can use these technologies today. So, where does this leave us? Today, CCS is the workhorse. Globally, CCS facilities already have the capacity to capture over 40 million tons of CO2 per year. That's a real, tangible impact. It's cheaper, it's more mature, and it can be attached to the biggest polluters to make an immediate dent in our emissions. For industries like cement and steel manufacturing, which have few other ways to decarbonize, CCS is an absolutely essential tool for the near future. DAC, on the other hand, is still in its infancy. The total amount of CO2 captured by all the DAC plants in the world today is only a few thousand tons per year. It's a tiny fraction of what CCS handles. It can remove the CO2 that was emitted decades ago. In the future, DAC could be critical for achieving net zero and even net negative emissions, lowering the concentration of CO2 in the atmosphere. The challenges for each are different. For CCS, the main hurdles are public acceptance, the long-term liability of storing CO2 underground, and the high upfront cost of building the infrastructure. For DAC, the challenge is almost entirely about cost and energy. CCS is the immediate treatment we can apply now to stop the bleeding, to stop pouring new emissions into the air from our biggest industrial sources. It's our most cost-effective tool today.